All right, welcome to the Explainer. Today, we're going to tackle one of programming's most elegant and, honestly, most misunderstood concepts, recursion. Okay, so here's the plan. We're going to start with the big idea, what recursion even is. Then we'll peek under the hood to see how the computer actually handles it. After that, we'll pit it against good old-fashioned loops, and we'll wrap up with some pro tips so you can actually use this stuff without breaking everything. All right, first up, what is recursion? Let's forget about code for a second and just get a feel for the idea itself. So, it all boils down to this one question. What if a function could call itself? I mean, think about that. A piece of code that, to get its job done, just calls a slightly smaller version of itself. It's a simple idea, but wow, it's powerful. It's kind of like looking into a mirror that's reflecting another mirror. You see this pattern that seems to just go on forever, right? Each reflection is a smaller, perfect copy of the one before it. That idea of self-similarity, that's the heart and soul of recursion. So, if we're going to put a label on it, here it is. Recursion is when a function calls itself to solve a smaller piece of the exact same problem. You're basically breaking a big, tough problem into bite-sized, identical subproblems until you hit one that's so simple the answer is just obvious. Okay, let's talk about the two golden rules. These are the non-negotiables. Every single recursive function has to follow these, or the whole thing just grumbles. First, you absolutely need a stop sign. We call this the base case. It's the condition that tells the function, okay, we're done here, no more calls. And second, you need the recursive case. This is the part where the function actually calls itself, but, and this is key, it does so with a slightly smaller or simpler problem to solve, inching it closer to that stop sign. And this is exactly why that base case is so critical. If you don't have a stop sign, what happens? The function just calls itself, and again, forever. It's like piling up an infinite stack of tasks that never get finished until your program's memory just gives up and crashes. And that, my friends, is the infamous Stack Overflow error. Now for the really cool part. How in the world does the computer keep track of all of these nested calls? It feels like magic, but it's all thanks to something called the call stack. Okay, let's trace this simple piece of C++ code. All it does is print numbers recursively. See that if n equals 0? That's our base case, our stop sign. And print n-1? That's the recursive call, making the problem smaller. So what happens when we kick this off and call print 3? So the computer uses what's called a call stack. Seriously, just picture stacking plates. First, our main call, print 3, goes on the bottom of the stack. But before it can finish, it calls print 2, so that gets stacked right on top. Then print 2 calls print 1, which goes on top of that. And finally, print 0 is at the very top of our stack. Each function is basically paused, just waiting for the one above it to finish its business. And here we go. Print 0 gets called. The function looks at n, sees it's 0, and boom, the base case is hit. It doesn't call itself again, it just executes that return statement. This is the turning point where everything starts to reverse. So, the base case is hit. Print 0 just returns. That plate comes off the stack. Now, print 1 gets to resume. It's already done its printing job, so it just finishes and returns. That plate comes off. Then, print 2 gets its turn to finish up. Poof, its plate is gone. And finally, our original call, print 3, can finish. The stack is clear. The printing actually happened on the way down into the recursion, not on the way back up. Okay. So if recursion has this whole complex stack thing going on, why not just use a simple loop? Iteration. Let's put them head to head. And this table really gets to the heart of it. There's a fundamental trade-off. Recursion can often be way more readable, more elegant. It can make complex problems look simple, but, and it's a big but, loops are almost always faster and use way less memory. So it's a classic battle, elegance and readability versus raw performance. And choosing the right one means knowing what you care about most for that specific job. So, with that trade-off in mind, where does recursion really shine? Where is it not just an option, but the best tool for the job? Well, recursion is the absolute natural choice when you're working with data that's, well, recursive itself. Think about a file system, right? Folders inside of folders inside of folders, or complex data structures like trees and graphs. For stuff like that, recursion is your best friend. Trying to navigate those things with a loop can turn your code into a confusing mess real quick, but a recursive function can do it cleanly and elegantly. All right, so we've seen the power, we've seen the dangers. How do you use this thing like a pro and not fall into the common traps? The most common beginner mistakes pretty much all come back to breaking those two golden rules. Forgetting the base case entirely is the big one. Or maybe you have one, but the condition is wrong, so it never gets hit. Or, and this one is sneaky, your recursive call doesn't actually make the problem any smaller. Any of these will send you spiraling into infinite recursion and, you guessed it, a stack overflow. Pros, on the other hand, treat recursion like a precision instrument. They make absolutely sure their base case is rock solid and impossible to miss. They tend to use it when they know the input size won't get crazy big. And for extra credit, they might use a cool trick called memoization, which is really just a fancy way of saying they cache results to avoid doing the same work over and over. They know its strengths, they respect its weaknesses, and they know when a simple loop is just the better call. So, if there's one thing you take away from all this, let it be this. The power of recursion is all tied up in that call stack. It's what lets it solve these complex, nested problems. But that power comes with one huge responsibility. You must have a base case to keep it all under control. So, in the end, is recursion elegant, genius, or a dangerous liability? Well, as you've probably figured out, it's neither. It's just a really sharp tool. And like any powerful tool, it's not about whether it's good or bad. It's about the skill of the craftsman, knowing exactly when to use it to create something elegant and when to reach for something else.